Hello everyone. Today's topic is about Fermi Dirac distribution function. First of all, what do you mean by carrier concentration? Carrier concentration means number of carriers per unit volume. Okay, if we know the carrier concentration, we can find the number of carriers per unit volume with the help of Fermi Dirac distribution function. The Fermi Dirac distribution function is denoted by the letter f of e, and that is normally defined as probability, that is the chance of finding electron in the energy level E. That is why this capital E is represented in the function f of e, and the f of e is stated as by the equation 1 by 1 plus e to the power e minus ef by kt, where e is the energy level which is chosen, ef is the Fermi energy or Fermi level, k is Boltzmann constant, which is equal to 1.38 into 10 to the power minus 23 joule per Kelvin, or it is also denoted by the value 8.6 into 10 to the power 5 electron volt per Kelvin. Both are the values correct for the Boltzmann constant, only the difference in the unit. And capital T that represent the absolute temperature in Kelvin. Now let us move to the continuation of Fermi Dirac distribution function. So here we note a level called Fermi level, which is denoted by the letter EF, and that is defined as the energy level where the probability of finding electron is 50%. That means if we are substituting the value of E is equal to EF, f of E becomes f of EF, that is equal to 1 by 2. That is already seen in the expression where we are substituting E as EF, and we will be getting the f of EF value as 1 by 2. We have two levels called EC and EV. As you know, the two band, conduction band and valence band. The bottom energy level of conduction band is called EC, and the top energy level of valence band is called EV, where f of EC is given as, that is probability of finding electron in the bottommost level of conduction band, that is f of EC is given as 0, and f of EV, that is probability of finding electron in the valence band, is equal to 1, because at T equal to 0 Kelvin for an intrinsic semiconductor, it is guaranteed that electrons will be present in the valence band, but it is not present in the conduction band until a temperature or any other external excitation is applied. So which is stated here, the probability of finding electron in conduction band is 0 and that of valence band is 1 at temperature T is equal to 0 Kelvin. But as temperature increases, this f of EC increases and f of EV decreases, because due to the increase in temperature, the electrons in the valence band break the covalent bond and they are jumping to the conduction band by overlapping the forbidden energy gap. So the probability of finding electron in the conduction band increases and that of valence band decreases as the temperature increasing process continues. So we can see that as electrons present in the conduction band, respectively the equal number of holes will also be appear in the valence band. Let us look at the graph. In the graph, it is a sharp square wave you can see here, that is nothing but for temperature T is equal to 0 Kelvin. Okay. Now, yes. So here T equal to 0 Kelvin, we can see a sharp square wave, but when the temperature is increasing, that is T1 which is greater than 0, f of EC increases from its 0 value and f of EV, that is decreasing from its maximum value of 1. As T2 increases, which is greater than T1, again the process repeats. But the main thing which is noted is about the Fermi level, which is having the Fermi Dirac distribution function for any curve that is equal to 1 by 2. Now the energy band diagram, here f of E, that is probability of finding electron, 1 minus f of E, that is probability of finding holes. Okay, here in the case of intrinsic semiconductor, the position of Fermi level is in the middle of EC and EV, that is in the middle of forbidden gap, that is in the middle of conduction band and valence band in the case of intrinsic semiconductor. where we can see the value of Fermi level EF should be equal to EI, that is intrinsic energy level. But in the case of extrinsic, the value of EF is nearer to conduction band, and in the case of p-type, the value of EF is nearer to valence band. Let us look at the energy band diagram. The intrinsic EF value, which is seen in the middle of EC and EV, and here we can see it is an intrinsic semiconductor, where the rightmost figure D, it is representing that the red shaded portion as electron concentration, the blue shaded portion as hole concentration. In the intrinsic semiconductor, whatever be the electron concentration in the conduction band should be exactly equal to the hole concentration in the valence band. And let us look at the diagram B, where we can see the density of state N of E, that is plotted with respect to the energy level, where N of E is exponentially increasing with energy. As N of E, the density of state increases, the energy level is also increases across the conduction band as well as for the valence band. And let us look at the third diagram, which is representing the variation of Fermi Dirac distribution function versus energy, where we can see the value of f of E is equal to 0, f of EF equal to 1 by 2, and f of EV, that is equal to 1. Okay, this red line indicate the electron concentration, and the blue line indicate hole concentration, that is 1 minus f of E. Now this is extrinsic, where the value of EF we can see nearer to conduction band, it is not in the middle, and we can see in the case of N-type, the number of electrons in the conduction band is more than number of holes in the valence band, because since it is N-type, electrons are the majority carriers and holes are the minority carriers. The excess, the free electrons, the majority carriers which are electrons, are getting only by the process called doping. So that in the figure number D of N-type, we can see the red shaded portion, which is electron concentration, that is larger than the hole concentration, which is stated as N greater than intrinsic carrier concentration Ni, and the P hole concentration, which is less than intrinsic carrier concentration Ni. Okay, and let us look at the next diagram, which is p-type semiconductor, where the position of Fermi level is nearer to the valence band, and since it is p-type, the holes are the majority carriers and electrons are the minority carriers. The number of electrons in the conduction band is less than the number of holes in the valence band because of the doping of acceptors. And in the figure number D of p-type, it is clearly understood that the electron concentration is less than Ni and the hole concentration P is greater than Ni. So this is about the Fermi Dirac distribution function.